Hello, welcome to Principles of Flight section 9. In this section we're going to move on and talk about stability in roll. So we'll cover the effect of dihedral, the effect of sweptback wings versus swept forward wings, the pendulum effect, Dutch roll instability, anhedral, directional stability, spiral instability, and then we'll take a look at some of the terminology so you can just get your head around that. First of all, dihedral. Well, dihedral is when the wings are inclined upwards, and the dihedral angle is the angle between the wing and the horizontal. And typically that's 3 to 5 degrees, and it provides stability in roll. When the aircraft is rolled or banked, the forces are out of balance, so the total reaction or the lifting force is acting vertically to the wing, but the weight is acting vertically down to the earth. And you can see that because they're out of balance, there is a resultant force which is acting along the wing, and this causes slip, and in turn that changes the relative airflow. So the airflow is now coming at an angle to the fuselage. Also, the actual act of rolling changes the angle of attack. So the downgoing wing has, during the time it's going down, has a higher angle of attack, and therefore it's going to generate more lift, whereas the upgoing wing is generating less lift. And this combination has a tendency to level the wings again, or if it's left to its own devices, it wants to do that. But of course this will only work if you're not near the stall. If you're near the stall, then the downgoing wing may have sufficiently high angle of attack to actually stall. The effect of dihedral on this sideways airflow can be seen here. There's a tendency for the glider to slip towards the lower wing. That changes the airflow, and you can see from this diagram here that there is forces on the upper surface of the wing versus the lower surface of the downwing, which also has a tendency to roll the glider's wings level again. Now we can look at sweepback versus swept forward, and why the designers choose to have one or the other. So swept forward wings, which are very common in gliders, is seen in the upper diagram on the right hand side, in this case of Blarney, and you can see quite a distinct sweep forward on that wing, as opposed to the lower diagram on the right hand side, which is a faster aircraft, and its wings are swept back. So we'll take a look at the two, and we'll start with sweep back. Sweep back influences stability in roll, because once the glider has rolled, it will slip towards the lower wing, and the effective wingspan has actually changed. So the lower wing has more effective wing acting as lift, as opposed to the upper wing, and this because the lower wing has more lift, it has a tendency to roll the glider back to level again. That's what it is trying to do. Whereas with a sweep forward wing, which is common in gliders, then when the glider slips, the lower wing has effectively got less wing presented to the airflow, and that means that the lower wing is generating less lift than the upper wing. So in fact, once it's rolled, it will want to roll further. So it's effectively unstable in roll. So gliders with a marked sweep forward have generally got more dihedral, and the dihedral is giving stability to the glider, and the sweep forward is reducing the stability, and to a large extent these two factors are working in opposition to each other. So you've got to ask, well, why did the designer even think about using a swept forward? Well, the reason is quite a practical one. Without sweep forward, we can see the diagram here, the pilot, the second pilot, the rear cockpit pilot, is sat more or less on the centre of gravity. So if he got out, it makes very little difference to the centre of gravity. And the centre of pressure is along the wing. And if the wing and the centre of pressure are going to be roughly in line, then the wing needs to be where the rear pilot is. Unfortunately, the view of the pilot when he's looking out for other aircraft is quite a narrow field of view, because the wing is in the way for a larger part. So what the designer does is he moves the root of the wing back and the tip of the wing forward, which leaves the centre of pressure pretty much in the same place, but that has effectively put the pilot further forward of the leading edge of the wing, and that gives him a better view out. And that's it. That's the reason that many gliders have got a swept forward design on the wing. Pendular stability is more common or more obvious in older gliders, and it's more pronounced in older gliders, but it's there in all gliders to some extent. And this is because the weight is acting down through the centre of gravity, and the lift or the total reaction is acting at 90 degrees to the wing and from the centre of pressure. And you can see if we roll the glider, we displace the centre of gravity, and it will want to return to its normal position with the centre of pressure and the centre of gravity in line with each other. Much more obvious, as I say, in older gliders than modern ones. If we look at extreme sweep back for a moment, this is a feature of high-speed aircraft, and after rolling, so in this example here, imagine the glider, the aircraft is rolled to the left, then the left wing, the port wing, is presenting much more airflow to the wing than the right, and that's because the aircraft is slipping. That sweep back then causes this correction, so that downgoing wing wants to go back up again, but it tends to overcorrect. So in overcorrecting, then the right wing will go down and the aircraft will then start to slip to the right, and that reverses the situation. Now the right wing wants to go back up, and this can build up into an oscillation which is called a Dutch roll oscillation. And in order to overcome this, the anhedral is built in, which is the opposite of dihedral, and that reduces the Dutch roll instability, which is why many of the military aircraft you see, for instance, have got these drooping wings. So the factors that are affecting stability in roll are: one, dihedral; secondly, wing swept forward or swept back; and the pendulous effect, or pendulum effect, of the wing versus the centre of gravity. Stability in yaw is very closely linked to the stability in roll, so they're interconnected in many ways. And basically, if the aircraft is slipping effectively towards the lower wing, and what will happen, of course, is the yaw spring will be quite clearly off from a practical point of view as the aircraft slips towards that lower wing. But now the profile of the aircraft becomes important, and if you look at these two diagrams on the left hand side, you can see that forward of the wing, the upper one has got a smaller area of a fuselage compared to the lower one, and if the aircraft is slipping, that has an effect on the weathercocking. So the fuselage, so if the aircraft is slipping towards that lower wing, the fuselage will try to behave like a weather vane, but of course the area in front of the cockpit area will have the opposite effect. And you can see the picture of a modern glider, rather strange shape, one we're not used to, and you can see there quite a large area in front of the wing, a very small profile on the fuselage, and a relatively small fin. If we just for a minute consider the wings level situation, so we're flying along wings level, and look at the diagram on the left, then you can see that the two things are going on. One, to give directional stability, the fin and the fuselage are in the airflow and being pushed back towards the to get it back in line with the relative airflow. But if you've got a large area in front of the wing, that's opposing that returning force. So the more area ahead of the wing, the less directionally stable the aircraft is, or weathercock stability is reduced. However, when a glider banks and slips, the glider also yaws towards the lower wing. So if you picture this, if you roll the glider with the ailerons without any rudder at all, the first thing that you'll see is adverse yaw. The nose will swing in the opposite direction. But then fairly soon you'll find that the nose of the glider will then swing in the direction of the roll. And that's the weathercocking. As that swing occurs, so the outer wing, the upper wing, is generating more lift, and therefore the roll increases. And this gives us a spiral instability. So gliders are generally relatively unstable in roll. So if we roll the glider, its roll will continue to increase, and as the bank increases, so the nose will pitch down. And this has the effect of the glider banks. If we just leave it, a spiral dive will develop where the speed will progressively increase as the bank increases and the nose pitches down. And because of all of that, the G will increase as well. And that's a spiral dive. So the combined effects of lateral stability and directional stability is what gives us spiral instability. So the more stable it is in these, then the more stable it is in spiral terms, and the less stable it is, and the more unstable it is in terms of spiral instability. So that brings me to terms, and we can easily get confused here. So I'd like for you just to pause and think. When we talk about stability in pitch, this is actually called longitudinal stability. And stability in roll is called lateral stability. Stability in yaw is called directional stability. And that's slightly different in terminology from the terms we use about the various axes. So in pitch, we would talk about, when we're talking about motion, we would be talking about lateral axis. In roll, we would be talking about the longitudinal axis, and in yaw, we would be talking about the normal axis. And remember that these axes are irrespective of the position of the Earth. So it doesn't matter if the glider is climbing upside down or pointing downwards or whatever, the axes are all in relation to the aircraft itself. Okay, so in summary, stability and roll we've talked about, dihedral we've looked at and the effect, sweep back versus sweep forward we've looked at, pendulum effects, Dutch roll instability we've touched on, anhedral we've looked at, directional stability and spiral instability, and then finally we looked at the various terminologies. I hope that you found that useful, and I will see you in section 10. Goodbye for now.